Welcome to the Deep Dive. Today, we're looking at something you've probably felt, even if you couldn't put a name to it. We all know how powerful large language models are, but there's this critical flaw under the hood.
They're static.
They're completely static. The moment they're deployed, they're basically prisoners of their own training data. They're frozen in time.
And that's the real tension, isn't it? They have this incredible ability to reason and create, but only about the world as it was when they were, for lack of a better word, born. They just can't do continual learning.
Right. They can't learn new things without this massive, disruptive, and, frankly, incredibly expensive process.
The total reboot.
So that's our mission for this deep dive. We've gone through a stack of research from places like Google and the world of neuroscience to explore a solution. It's a paradigm shift called nested learning, or NL for short.
And it's really about rethinking AI systems from the ground up to be truly adaptive, to almost give them an internal sense of time.
And it's a problem we have to solve because this inability to learn new things without forgetting the old, it's a major roadblock.
It's called catastrophic forgetting. And it's this huge design flaw that really limits how these AIs can integrate into our, dynamic world.
There's an analogy in the source material that I found, well, kind of chilling. It compares this problem to a real neurological condition.
Anterograde amnesia.
Exactly. The model can remember everything before its last training run perfectly. Its long-term memory is solid, but it can't form any new long-term memories.
Any new information just exists in its immediate context window.
Yeah.
And then, poof, it's gone forever.
And that amnesia has a huge, huge impact on the bottom line. It's not just a technical problem, it's a serious financial one.
And that financial pressure is what's really making the search for a new architecture so urgent.
So let's just lay out the economic reality here. First off, the retraining costs they're just prohibitive for most companies to do continuously.
We're talking big numbers.
Huge. GPT-3's initial training was something like 3,640 petaflop days, the estimated cost. About $4.6 million.
For one training run.
One run. And we found this case study of a multinational financial firm. They're spending over $2.3 million a year just to refresh their customer service AI.
And most of that is just raw compute costs, just brute force retraining.
But it's not just the money, is it? It's the time. Because these models are so brittle, you have this massive 6 to 8 week cycle to refresh them.
Right, you have to collect the data, run the model, validate it, deploy it.
And that whole time, your business is waiting. That operational lag is a killer for dynamic industries.
We saw a great example of that, a European retailer.
Yeah.
They actually quantified what that delay cost them in their seasonal product category.
And the number was?
About 2.1% of revenue, all because their AI couldn't adapt quickly enough to new trends.
And that lag is made so much worse by the core technical problem that nested learning is trying to fix.
Catastrophic forgetting. It's this idea that when you fine-tune a model on a new task, you actually degrade its performance on the old tasks it was already good at.
So let's make that real. What does that look like in a high-stakes environment?
Well, think about healthcare. A hospital system fine-tuned its AI model to get better at detecting sepsis, using new criteria, a really important update.
Okay, sounds good so far.
But in doing that, they saw a 12% drop in accuracy for diagnosing pneumonia, which was a task the model was already an expert on.
Wow. So they fixed one problem but created a completely new one.
And they had to pull the model, do costly remediation. It just destroys trust.
And that leads to user friction, doesn't it? We saw examples with oncologists whose field is constantly evolving.
Right. Their AI decision support tools are often 9 to 14 months behind the latest research. So the doctor has to mentally correct the AI's outdated advice.
Which kind of defeats the whole purpose of having an AI assistant in the first place.
Exactly. And the end result is that people just don't use it. Gartner found that 43% of enterprise AI projects face resistance. And why? Because users just see them as stale.
So we have this crisis, AI that's static, expensive to update, and in dynamic fields, not very trustworthy. How does nested learning propose to fix this?
Well, this is the big conceptual leap. NL says we have to stop thinking about models as just a static stack of layers.
Okay.
Instead, we should see them as integrated systems of nested optimization problems that all operate at different speeds, different temporal frequencies.
So it's all about how often different parts of the model change.
That's the heart of it. The insight is that every single component, from the attention mechanism all the way down to the optimizer, is basically acting as a kind of memory. It's compressing a flow of information. NL just organizes them by their update frequency.
So fast updating parts are like an inner problem, and the slow, stable parts are an outer one. That sounds a lot like it's borrowing from neuroscience.
It is. It's a direct mirror of how our brains work. You
Yeah.
have these very fast gamma waves for, say, immediate sensory input, your working memory, and then you have much slower delta waves that are responsible for consolidating things into long-term memory.
So NL is trying to build that multi-speed structure directly into the AI's architecture.
And here's the thing that makes it click. Even in a standard basic model you're training right now, you can already see 3 of these nested levels. We just never designed them that way on purpose.
Ah, so we've been doing it by accident. What are the 3 levels?
Okay, so level 1, the fastest, is the attention mechanism. It's updating with every single token. It's your working memory.
Makes sense.
Level 2, medium speed, is the network parameters themselves. They update with every training example or batch. This is where most learning happens now.
And the slowest.
Level 3, that's the momentum terms in your optimizer, like Atom. They accumulate gradients over many examples before making a big, stabilizing update. They are, without us realizing it, an implicit long-term memory buffer.
So if I'm hearing you right, the standard transformer models that everyone uses are limited because they really only operate at 2 of those speeds, attention and parameters. We're not really using that level 3, that slow memory, strategically.
We're totally underutilizing it. And worse, we think of optimizers like Atom as just a math formula. NL shows us they're actually memory modules,
Yeah.
but they only have 1 speed, which isn't enough for stable continuous learning.
Okay, so nested learning gives us the framework to see the problem. Let's get to the solutions. What does the evidence say we should be building?
Well, the principles of NL point to 3 big architectural innovations. The first one tackles that slow, level 3 memory. It's called deep optimizers with enhanced memory architecture.
So we're not just optimizing the network anymore, we're optimizing the optimizer itself. How does it work?
Well, traditional momentum is pretty simple. It just averages past gradients.
Yeah.
Deep momentum gradient descent, or DMGD, replaces that simple average with a whole multi-layer network.
Whoa.
Yeah. So the optimizer can learn complex, nonlinear patterns in how the model should learn. It's basically learning how to filter out the noise and keep the important trends. It's learning how to learn better.
And if the optimizer is smarter, what does that get you in the real world?
Big efficiency gains. DMGD was 15 to 23% faster at converging on language tasks than Atom. We saw a pharmaceutical company use this, and they cut their training time for new drug models by 31%. That translated to about $180,000 a year in compute savings. That directly hits that cost problem we started with.
That's a huge deal for training. But what about after deployment? What's the next innovation for that?
That brings us to the self-modifying sequence model. The best example is an architecture called HOPUS. Hierarchical optimization with persistent evolution. It's basically putting meta learning right into the model's architecture. So the system doesn't just update its knowledge, it actively learns and adjusts its own update rules as it goes.
So the model is changing how fast it learns depending on the data that's coming in?
Precisely. HOPE uses these rapid, intermediate, and slow layers, and the results are pretty clear. A 1.3 billion parameter HOPE model was about 18% better on a key benchmark than a standard transformer. It's just much more reliable.
And there was a great case study for this one, wasn't there?
There was. A financial services firm used HOPE to generate real-time market commentary. And because it could modify its own learning rules, it just kept up. It adapted to new jargon, weird market events.
While the standard models got stale.
Exactly. The standard model saw a 12% drop in relevance over 6 months. HOPE's performance just stayed flat, consistently high. It never got stale.
Okay, so that handles adaptation. Let's hit catastrophic forgetting head-on with the third innovation, continuum memory system.
Right. This is about getting away from the simple binary of working memory versus long-term memory. Continuum memory creates a whole spectrum of memory scales, fast, medium, slow, and so on.
But the real magic trick to stop the amnesia is something else, right?
It is. The architectural fix is that each of these memory components has its own dedicated gradient flow. They're structurally isolated from each other.
Okay, that sounds important. Why is that isolation the key?
Think of it like a plumbing system with separate pipes. If the fast pipe gets a lot of noisy updates, like a user correcting a single typo, that noise can't bleed over into the slow pipe that holds your fundamental knowledge.
So you protect the core knowledge from the chaos of real-time updates.
You completely prevent the interference that causes catastrophic forgetting in the first place.
And what did that look like in a real system?
A global logistics company built one. They had a 3-tier system. a rapid memory for real-time traffic that updated every 15 minutes, a medium memory for daily patterns, updated nightly, and a slow memory for seasonal trends, updated monthly.
And the results.
They cut their computational cost by 58% compared to their old full retraining method,
Hmm.
and they got basically the same accuracy improvements, stability and efficiency.
So these technical breakthroughs are incredible, but what does this mean for, an actual organization? This seems to force a whole new way of thinking about knowledge management.
It absolutely forces you to be more strategic. You can't just have one big feedback bucket anymore. You have to route feedback to the right time scale.
So a frontline user pointing out a typo.
That's a rapid integration signal, goes to the fast memory, gets consolidated hourly, and that's it.
But if you get a major update to, say, an industry regulation.
That's a slow integration signal. It has to be validated,
Hmm.
and it updates the slow foundational memory layer. You can't let a single user comment accidentally rewrite your company's core compliance logic.
Right. And this creates some new challenges for governance, doesn't it, when the system is constantly changing itself?
It really does. You have to start thinking about temporal scope of accountability. If the system makes a bad call, was it because of a bad update from today or a flawed principle from 6 months ago?
It makes the audit trail much more complex.
It does. You need to be able to trace exactly which piece of information at which speed led to a decision. And beyond that, you have to set limits. An AI that can change anything about itself is an uncontrollable AI.
And that's where this idea of bounded adaptation zones comes in.
Correct. You define what's allowed to change. Maybe the rapid memory can adapt the model's tone and phrasing, but the slow memory, the one with core business logic, that has to be locked down. It needs human sign-off for any change.
And this all points to a pretty big shift for the AI workforce itself.
It does. We're moving away from just training models. The new skills are in multi-scale architecture design and optimizer customization. You're not just an ML engineer, you're designing an entire learning ecosystem.
So, wrapping this all up, what's the key takeaway for you as you think about the next wave of AI?
I think the core idea is that we are shifting from simple architectural depth, just stacking more layers, to something new, temporal depth.
Designing systems with different speeds of learning built right in from the start.
And the evidence is really compelling. The organizations using these ideas are seeing 50–60% cost reductions, they're maintaining accuracy, and they're finally getting systems that can truly adapt without breaking.
So this ability to evolve is becoming table stakes, not just a nice to have. Which leads us to the provocative thought we want to leave you with.
Go for it.
Okay, so if today's AI is frozen and static, and nested learning gives us a clear path for systems to evolve after they're deployed, what are the ethical implications when our regulatory frameworks can't possibly keep up with a system that is continuously adapting itself at multiple speeds? The stability and the speed of change are now architectural choices, and that's going to require a whole new way of thinking about trust, audit, and control. Think about that as this rolls out.